start the good old recording. And let's go ahead and start the screen share. That'd be a good idea, Dylan. Let's go and let's just hop right in. Hopefully we get a few more people. I think the fact that I sent the ping out an hour and a half before the session instead of right before is like maybe causing people to sort of forget or like be a bit late hopping in, but
who knows?
Yeah. Or maybe it'll be just us and we'll get a solid, hour 15 and just solid work. So, obviously,
I can remember most of this.
yeah. Honestly, for the final quizzes tomorrow, you just have to worry about the main concepts, and there's going to be generally one or two takeaway things for each section of the class that you want to focus on. Speaking of which, the first section of the class, thermo. What do you need to know for the quizzes tomorrow for thermo?
Judging that you all didn't even pull up the thermo is none.
Nothing. Exactly. Don't have to worry about thermo at all. I guess just maybe generally remembering the concept of potential energy. I don't know. But
To
so
be
yeah.
honest, out of everything, thermo was the easiest of the class.
Yeah.
It would have been nice to at least get a little bit on that, like, guaranteed points, but I'm okay with it.
Yeah. So the first part that you're really going to actually have to worry about is electricity, units 5 through 10. So when you think back to electricity, what are the main things you remember? What are like, let's say 2 to 3 main things you remember being takeaways from electricity?
I mean, the biggest one is Gauss's law.
Gauss's law, exactly. What is Gauss's law?
Why do I not have that on the... okay. I really don't know why I don't have it on the actual sheet. I probably do have it somewhere in my notes, but it's going to take forever to find.
Gauss's law. G's law.
Where the heck is it in the class notes? I think it was Unit 7. Class 7, I meant.
Wait, am I just noticing? There's no Unit 7 on the formula sheet.
Huh.
It just goes straight 5, 6, 8, 9, 10. The hell? I'm curious, what was Unit 7? Or did he just, accidentally skip a number?
Give me a minute. Everything always likes to take his sweet time on this. Unit 7, electric flux and field lines.
Okay, that makes sense. So, there's not really... It was mainly the concept, and there wasn't really, any specific equation, apart from the equation that you covered in Unit 8.
Okay, yeah, then Unit 8 would be the Gauss's law once everything starts to load up again.
Mm-hmm.
I mean, I'm happy I have a laptop and a monitor right next to me, so that way I can actually have notes right here while also work on my laptop.
Hell yeah.
It can be slow. I mean, not laptop, the desktop.
Yeah.
There it is.
I am never going to be able to go back to one monitor. I got 2 monitors for my desktop. Never going back.
Okay. To be honest, that was my first guess, and I would have been right. It would be the surface integral, the closed surface integral, I should say, of the electric field dot dA, which equals the Q enclosed over E naught.
Yep. So the closed surface integral of E dot dA, which, by the way, this is the electric flux. Remember how we were just looking at magnetic flux? Essentially, the amount of field lines through a surface is equal to the charge enclosed within the surface over epsilon naught. That's wonderful. We can use that to calculate the, if we know the field strength and the field lines through every point on a surface, we can find the enclosed charge inside. And that's cool, but that's not really helpful, right? What sort of situations do we actually use Gauss's law in, and what do we use them for?
It's supposed to be symmetry surfaces, if I remember correctly.
Yep, surfaces using with symmetry. And what do we actually use Gauss's law for?
Okay, so it's easier for that. We use it for... Um, well, we use it for the electric field, I believe.
Exactly. We use it to find the electric field.
Okay, then. It's just that. All right.
And so how would we do that? You want to just run me through real quick?
That's the formula underneath that. So that should be the electric field is equal to whatever that symbol means again over 2 E naught.
What? For literally any situation?
uh. Oh well. Okay. Forgot Kumla's law. Uh.
Coulomb's law?
Coulombs. There we go.
Coulomb's, yes. What is Coulomb's law?
Uh. Well, the integral of dE, which is also equal to k integral of dq over r squared, and then I think that r is supposed to be that extra r. Oh, okay. Yeah, it's supposed to be. It's equal to k big Q over r squared, and then I believe that r is supposed to be direction.
Mm-hmm. Yeah. So essentially,
R hat is the direction.
yeah. So essentially, we can use Gauss's law for symmetrical cases to find the electric field. For a spherically symmetric case, dot product goes away, E times dA, E is constant, comes out, integral dA is just the area. So then we get our electric field is equal to 1 over 4 pi epsilon naught with the 4 pi.
Right, that's what K. Yeah.
Yep. And then we have Q, and just use big Q instead of Q enclosed, over r squared. And then I'll add a little r hat to signify the direction. 4 pi r squared comes from the area, epsilon naught Q, and this 1 over 4 pi epsilon naught is the same thing as K. That's for a spherical case. What happens if we have what's another type of symmetry we have for Gauss's law?
Would that be cylindrical?
Cylindrical, yep. And so what happens with a cylindrical case?
Ooh, now that one's going to be... Is that on this one? Oh, it will be in the next unit. Let's see. Trying to remember off the top of my head. Uh, Dang, I really can't remember on the top of my head.
All right, so run through it. So we have...
Is that dV over dx? No, that's something else. That's
No.
way too...
Yeah. So let's run through it step by step, right? What happens with our dot product here?
Um... It becomes multiple parts. Like there's stuff that for cylindrical there'd be stuff that's perpendicular to area and the other one would be parallel to the area.
Yeah, exactly. So we have our end caps, essentially, of our Gaussian cylinder, and then we have the barrel itself. So you mentioned parallel and perpendicular. So what happens with the end caps? What happens to E dot dA for the end caps?
And okay, I just found everything for that too now. But if the magnetic field is going into the end caps in the same direction, like left to right, it would be 0. Right? Because that would be parallel to each other? Or is that... Nah, probably... No, that's...
So for a cylindrically symmetric case, we're just going to worry about cylindrical symmetry. So like we have a line of charge. What direction is the electric field in?
Is this where we need to use right-hand rule again?
Electric field.
Oh, right. Which way's the positive charge going again?
Well, yeah, we'll assume the whole line is positive.
So okay, and then that means all of that is going out.
Exactly. The electric field is always going to be going straight outward from our line of charge. So for the end caps, what is the electric field .da? What direction is the area vector for the left end cap?
Uh, left.
Exactly. It's direct rate straight outward, perpendicular to the surface.
Okay. So I was just getting I myself was getting that one wrong. Okay then. So they're perpendicular to each other.
Mm-hmm. So what's the dot product become?
I believe that would become E times A. And that A will be a circle.
What is the dot product once again? It's the magnitudes.
Yeah, it's it's the magnitudes of A, B, and then you have to do the cosine.
Cosine. What's the cosine of 90 degrees?
0. I was thinking
Zero.
sine.
Yeah, you're
So,
getting.
okay, I was mixing it up with the cross product or something like that.
You've just exactly. You've just been doing too much magnetism the last 2 weeks.
That's probably where I'm getting those confused. Yeah, so I can already tell that if people are going to mess up so much on those,
Yep.
it might be better to just stick with circuits. If you need only a little bit for a B, make sure you get enough for circuits because at the very least, that's the least confusing of the three.
Yep. So we have our E.DA is 0 for the end caps, and what about the barrel?
That one is parallel, and that means it will have. It will be E times A.
And what's the area of our barrel?
That would be a cylindrical surface.
Mm-hmm.
So that would be 2 pi RL.
Exactly. So then we just divide the area over, and we get our electric field is equal to 1 over 4 pi epsilon naught. And then because it's just 2 pi L, we'll have the other 2 up here. I just like grouping the 1 over 4 pi epsilon naught because that's equal to K. And then we have 2. And then what is the enclosed charge within our Gaussian surface here? Let's say the line of charge has a charge per unit length lambda.
So wouldn't that be the lambda enclosed?
Times what?
So that would be 2. We're looking at the one at unit 6, correct?
Perhaps.
So lambda can equal Q over L.
So that means Q is...
Well, I mean, the Q is the charge.
Mm-hmm. And that's what we want. We want the enclosed charge.
Okay, lambda times L.
Exactly. Lambda times L. And then, but we're dividing by L from the area. So it ends up canceling out. And so then we end up just having... So we have lambda times L over epsilon naught. And then we divide by 2 pi RL. The L's cancel out. And we have 1 over 2 is the same thing as 2 over 4. Boom. That is our electric field for a cylindrical surface. And what about our last type of symmetry?
This has to do with capacitors, right? The parallel plates?
Yes.
Okay, then.
So how do we derive the electric field using Gauss's law for an infinite sheet of charge?
Oh, and that was the one I was trying to say the other way. Sigma, I believe it's called, right?
Mm-hmm.
Sigma over 2 epsilon naught.
And how would we get that?
Sigma can equal to Q over A.
Mm-hmm. So what is our Gaussian surface going to look like?
Gaussian surface? Doesn't that depend?
What do you mean?
Uh, hmm. Oh, never mind. I see now. I was actually trying to find that on the sheet, and I just glanced over it. I guess so. It's cylindrical shell. Sorry, the Gaussian surface is the cylindrical shell. I don't know. I
Yep,
was looking at everything else underneath it.
exactly. It's a cylindrical shell that essentially sort of pokes its head through both sides of our infinite sheet. So what's the enclosed charge?
uh, there, right in the middle of the cylinder.
Exactly. It's our Q enclosed is sigma times our area here, which would be the area of a single end cap. So
Yeah,
we'll call it
a
A.
circle.
Yeah, it's a circle. We'll just call it A because realistically, you don't have to use a cylindrical shell. You could use a triangle if you wanted.
Oh, lol.
You could use a rectangular prism if you wanted. It literally doesn't matter. So we'll call it A. So the enclosed charge is Q times A. And what is E dot dA? First of all, what direction is our electric field in?
Should it be perpendicular?
Exactly. It goes straight outward from our infinite sheet. So what's E dot dA for the barrel?
I want to say 0.
And why would it be 0?
Cosine 90.
Exactly.
Okay.
dA for any point on the barrel is always going to be perpendicular to the electric field. So E dot dA is 0. What about the end caps?
They both will have. There will be field on the left and the right side of equal magnitude, but opposite direction.
Mm-hmm. So
In this scenario, yes.
so there's, yeah, you're right. On at the end cap on each side, there's the same magnitude electric field, and one is going to the left, one is going to the right. What direction are the area vectors for our end caps?
Same direction.
Exactly, same direction. So for each end cap, our E dot dA is just E times the area, right?
Yeah.
And then we just have to add them together, so it's 2EA. And so we just have to divide our area, which is 2A, over our enclosed charge, which is sigma times A. And so then we get E is equal to sigma over 2 epsilon naught. The area ends up canceling out. And we'll call this n hat, just for my sake. You can ignore that. N hat generally refers to like outwards from a surface.
Okay.
But that's just me. So yeah, that is how we get our electric field using Gauss's law for all symmetric cases. And honestly, that's probably most of what you'll have to worry about on your exam tomorrow. There's just one other thing that I think you might want to brush up on. And it involves Unit 10. Gonna have to know how to potentially calculate a potential difference. And go from an electric field to a potential difference, or from a potential difference to an electric field. So, how would we find the potential difference between this point and this point? Let's say they're, 2 meters apart.
Well, let's see. The potential difference is normally VB minus VA, which would equal to the negative integral of AB which is inside the integral, E dot dl.
Exactly. So we would take a line integral of E dot dl, which line integral just, in this case, it just means E dot dx. So E dot dx, our electric field is in the positive x direction. It's off to the right. So E dot dx just becomes E times dx. I think you would agree on that.
Yeah.
What is our electric field here?
Shouldn't it be going the same direction?
What is the magnitude of the electric field?
dv over dx? Or am I too far again? Oh, okay, yeah. I'm going to say, but it's zooming in too far. Sigma over 2 epsilon naught.
Exactly. That's a constant. Sigma is a constant. It's just has to do with the charge density of the sheet. Epsilon naught is a constant. So E is a constant, so it's just our electric field times the distance in this case. And then a negative sign, because if we go from here this way, we're going in the direction of the electric field, and anytime you're traveling in the direction of the electric field, the potential is going to decrease. And vice versa. That's why we have negative integral of E dot dl, and why we have negative dv dx. And so then, obviously, if you wanted to reverse the integral, you would take E is equal to negative dv dx. You know, a derivative is the opposite of an integral. That's pretty much it for electricity, honestly. I don't think there's going to be much else you're going to have to worry about. It's mainly just going to be knowing how to use Gauss's law and understanding potential and understanding conductors versus insulators.
And don't mix them up from the magnetic fields.
Yep, don't get dot products mixed up with cross products, and don't try to use right-hand rules with electric fields. So what's the difference between an insulator and a conductor?
Conductor, the charges move freely, while insulators, they're stuck in place.
So by consequence, because of that, what happens?
Since the charges are moving freely, the electric field in the inside is zero?
Exactly. And so what does that mean about the potential difference? Or what does that mean about the potential anywhere inside a conductor?
Wouldn't that also equal zero?
Not zero, but it's all going to be the same. So the potential difference, the potential difference from any point inside a conductor to anywhere else in the conductor is going to be zero because the potential is constant.
Okay.
Yay! That's pretty much electricity. Honestly, Gauss's law, potential, that's all you need to worry about. The next main thing you guys had to deal with was circuits and capacitors.
At least we got a little bit of a refresher on that.
Exactly. You guys got some nice little practice with that with inductors on Monday. So
I would have gotten an A on that quiz if I didn't misread one letter. I literally thought it was light bulb B, not light bulb A. I was like, damn. I thought it was weird too, because wait, it is supposed to go out. Didn't it say B? Whatever. It just said whatever, and I double checked everything too. I even double read everything.
You choked.
Yeah, except for that one question. I did mess up on one other question, but that was just something I was like, I wasn't 100% sure on either way.
You choked in the final round. You choked in the home stretch.
It's still, it was 9 out of 12 instead of 11 out of 12. Either way, but the 11 out of 12 I believe would have guaranteed me the B in the class no matter what.
See, you've opened yourself the door to absolutely disappoint. But regardless,
all I need is 0.5 of the percentage of final. I don't think I'm.
Yeah, you'll be fine.
Yeah.
So, Circuits.
Yeah.
Circuits. So the main things that you guys saw with circuits is essentially you're just usually going to have to break down circuits with a bunch of resistors or with resistors and capacitors. So,
And it's either by series and parallel and all
yep.
that.
So how do you add together capacitors in series?
Okay, I need to make sure because it's the opposite. So the resistors in series, it should be 1 over R1 plus 1 over R2, which basically you can turn into R1, R2 over R1 plus R2.
Is that for for resistors in series?
Uh, let's see, Unit 11, right? Let me double check that because, like I said, I think it's opposite at one point.
Yeah, so resistors and capacitors are opposites. So for capacitors in series, how do you get the total net capacitance?
Uh, okay, capacitance would equal the charge over the change in, and I believe the V in this case is volts.
Yep, the
So change in volts.
potential difference or voltage or however you want to put it.
So yeah, or the other way you could calculate is the absolute C is equal to absolute naught times A over D, which I believe A is supposed to be the area and D is supposed to be the distance.
Yep, that's how you calculate the capacitance for a single capacitor. The thing is, I don't think you're going to have to worry about that too much for tomorrow's quizzes. I think you're just going to be mostly focused. You might have one problem where you have to find the total net capacitance or net resistance in a circuit. And he'll give you the capacitances of each individual capacitor. So if you know C1 and you know C2, and they are, if I can draw straight lines, they are in series with one another. How do you find the total net capacitance?
I know one of them you add them, and then the other, I mean, like you add them in either one. But let's see, it's series. Okay, here we go. Finally, it's 1 over C. It's 1 over C1 plus 1 over C2.
Exactly, and then to the power of -1. So
Yeah. So okay, it was capacitance and resistors that were different. That's what I was trying to figure out.
yeah. So for series capacitors, it's that whole, it's 1 over C1 plus 1 over C2 to the -1, or in other words, C1 times C2, it's C not a G, C1 plus C2.
Yeah. This one's just way better.
Yeah, I love this. This is so much better. And so then for parallel,
You just add the two,
exactly, it's just C1 plus C2. So I'm just going to
and
make,
then
I'm
and
gonna
then
make
the
a
other
little
note,
drawing.
and the other notes that will come in handy is if it's in series, the charges are equal. If it's in parallel, the voltage is equal.
Exactly. So
That itself does not change for resistors or capacitors.
Q1 equals Q2, V1 equals V2. Those are good notes to have.
Mm-hmm.
Anything else you want to say that you think is going to be important for capacitors tomorrow?
Would that be dielectrics?
Dielectrics. So what is a dielectric?
So, don't fully remember the actual thing, but what it does is supposed to increase the capacitance and the potential energy. Correct?
Mm-hmm. So, what happens if we stick a dielectric with, let's say, a constant dielectric constant of like 5 inside a capacitor?
Wouldn't that be 5 times the regular capacitance?
Mm-hmm. So, what happens to the voltage across the capacitor?
Um, hmm.
If it's just a single capacitor connected to a single battery.
I think the voltage stays the same, right?
Yeah. So what
Okay,
happen? So what happens to the charge?
that should increase.
Should increase exactly. C is equal to Q over V, and
Yeah,
because
yeah, yeah. Now
voltage.
that's coming back.
Yep, exactly. And so what happens to the potential energy stored?
Increases.
Exactly. It's going to increase by 5 times. Half CV squared. C increases 5 times. V does not change. And you obviously calculate the capacitance by multiplying it by the dielectric constant. Honestly, it's pretty simple, and you probably won't have to worry about it too much. You might see
Yeah, yeah.
one tiny little thing. So then for resistors.
All right, resistors is the opposite when it comes to capacitors.
Mm-hmm.
Resistors in series, that's when you add them together, just add them together. So R12 is equal to R1 plus R2.
Mm-hmm.
The current, I believe in this case, this is when currents comes in as well, right? So uh, the current in series should equal each other as well.
So
I1,
I1 equals I2.
and then you'll have to add the voltage together to get the voltage equivalence.
Yep,
And then
exactly.
the ones in parallel is the one you have to do R1 R2 over R1 plus R2.
Yep, exactly.
Voltage stays the same, and you just have to add the currents together to get it.
Yep, V1 is equal to V2. Good things to write down. Honestly,
Yeah,
I think you're gonna do completely fine on the circuits part.
yeah. Honestly, the circuits one's the one I'm most comfortable on. I mean,
Mm-hmm.
literally, I would have gotten an A on that quiz if I just did not misread that one letter. It was just one letter, and that's what pisses me off the most. I had 20 extra minutes left too, and I did triple check everything. I just didn't reread that question. Uh,
Unfortunate.
it does, yeah. I thought at the very least maybe he'll give a pity point, but no.
No. So,
Because I was right about shining immediately and be in constant brightness, but it just gets brighter, not dimmer.
mhm.
Because I was focusing on B, not A.
So what happens when you have resistors and capacitors together? Hmm.
And that's where the fun comes in. Okay, that should still follow some of the same rules. Let's see.
So let's say we just have like, I don't know, we'll have a
Is this one with, would this be an open switch type of thing or not?
potentially. So let's
Oh,
say we're going to
really?
we're going to have a resistor and a capacitor together, and we're going to have our little switch right here. Trying to figure out how I want to draw this.
That's an interesting switch placement.
Let's do this. So we have our switch here
Okay. All right then.
that can go ahead and switch back and forth here. Wait, no. This is bad. I can't. I'm dumb. Hold up. Wait.
That will not work well because there will be
Ah.
there won't be any flow whatsoever on that one.
Wait, hold up. Let me think. What does I try to do here? Okay, wait. I think I got it. I think I got it.
That would
Uh,
have been a good example for an inductor if I remember, but capacitor may be a little bit different.
all right, here's our switch. It goes right here.
There we go.
So it's going to be here for a long time. What is going to happen in our circuit?
Okay, at first when it if at first
We're not
when
gonna
it,
we're not gonna worry about that first. We're starting initially after it's been here for a long time.
all right, then it's an open circuit.
So
The capacitor is an open circuit.
the, So what does that mean about the current in the circuit?
I believe there's no current.
No current. So what's the voltage drop across the capacitor?
0.
Eh.
Yeah, that as soon as I said that, I was like, uh, should if it's not 0, it would be at its maximum point.
Which would be
The battery?
exactly same voltage as the battery. And because there's no current in the capacitor, because there's no current in the entire circuit, there's no current flowing through the resistor, which means there's no voltage drop across the resistor.
Okay.
Take a moment to sip water. Stay hydrated.
Too bad I don't have one on me right now. It's all the way downstairs, and I don't feel like.
I drink like a gallon and a half of water a day. All right. So, what happens then when we go ahead and flip the switch?
It acts like a battery.
Exactly. Our capacitor initially acts like a battery. So, what's the current in our circuit?
It should be. No, that's inductors. I was about to say it's going to be the same current as it was before, but the current would have been 0. So, so the current should be at max. So what? So I guess I would say whatever the current was initially when it was first closed.
Yeah. And what would that end up being?
Let's see if we know. Okay.
Here, I'll give you some values here. I'll give you V, I'll give you R, and I'll give you C.
Okay. Yeah. So. Yeah, just trying to remember how everything would go. So P. Well, I wish I could say we can use P is equal to IV and all that, but we don't know the power as well. So.
And does the
There it is. V is okay. That is on here. V is equal to IR.
exactly.
We know the voltage and we know the resistance.
So we know the current is just going to be V over R.
Yes.
And then after a very long time,
it will decrease and decrease till it hits 0. Because it will lose all the charge, all the current, and all the voltage.
And in what way is it going to decrease?
That damn exponential one.
Yeah, it's going to be an exponential decrease to 0. So it's going to look something like this. This is e to the negative x, right? It's going to be some sort of e to the, not x, it's going to be negative t.
Oh, yeah, in this case it would be t, yeah.
And what else would have to be in this equation? How quickly does it decrease?
Quick?
Like, how would we actually find how quickly? Like, how would we... Is it just e to the negative t and that's straight up our equation? Or do we have to take some sort of a time constant into account?
There it is. Is it? I believe this case is called tau.
Mm-hmm.
Okay, so it's tau, and that's R equivalent times C equivalent.
Which in this case would just be RC. And how would we fit it into this equation?
Well, it'll be within the exponential. Would that be over RC? Or it's one or the other. It's either RC over T or T over RC.
It's gonna be T over RC. It's T.
Okay.
It's T over tau, where tau in this case is RC. Boom! Magic, amazing. That's the current, and then obviously we could also find the charge on the capacitor, which would decrease similarly. We could find the voltage across the capacitor, which is also going to decrease similarly. And now what about when we then flip the switch back down and we reconnect the battery?
It will act like a wire. It will start gaining the charge, the current.
Is
It
it
will have it will have a max current, and then the current will decrease, but the inside the capacitance, the charges will keep building up.
exactly? So the current is going to do the same thing. We're just going to start at a initial value and decrease down to zero. But as you said, the charge is going to exponentially increase and approach a maximum value.
And that's where the 1 minus e to the negative t over tau comes from.
Exactly. 1 minus e to the negative t over tau. And so, obviously, not just the charge, but also the voltage across the capacitor also does the same thing. Yay! That's resistors and capacitors together. Now, there's one more part of the class that we covered, and you've been thinking that we've still been doing it this whole session, so I'm going to be real disappointed if you start getting confused now. Because your mind couldn't stop thinking about it earlier when we were thinking about electricity. Magnetism! Let's go!
And I'll still mess it up.
So, what do you think the main takeaways from magnetism, for the magnetism part of the class, were?
I wish I can remember some of the names. Give me a minute.
Don't talk about names. Just like mention formulas, because there's not really like names. There's only a
law.
few.
That was roughly 1, I believe.
What was that?
Ampere's law.
Ampere's law.
Because I believe that's supposed to be similar to Gauss's law.
Exactly.
And of course, before I go into any right-hand rules.
Right-hand rules. God bless. I'm just gonna write that in big letters. Right-hand rules.
Yeah. So Ampere's law and then motional EMS were definitely the big ones.
Exactly. Those are the two I think are most important. So you need to understand motional EMF, which is derived from what other law? I think should be better to focus more generally on.
Would that be the flux?
The flux, which is used in what law?
That's the one I can't... the one thing I just said, Ampere's law.
Nope, flux isn't used in Ampere's law. Ampere's law is how you calculate magnetic field due to a symmetric wire carrying current.
Oh, right. Where the heck's that law then? Motional EMF, it should be in Unit 20.
Unit 21. It's right underneath the flux equation. And it has a little guy named Michael. Faraday's law. Faraday's law and Ampere's law, I think, are the two main ones that you should focus on for magnetism. So what's Ampere's law?
I just had that up too. God damn it.
I thought you had like 3 monitors.
2. I can have a bunch of windows open if I wanted to, but yeah. It's that not Unit 21 because I believe Ampere's law is the closed integral. So the closed integral of the magnetic field times dl of dot dl, which becomes U naught times I enclosed.
Exactly. So the closed integral of b dot dl is equal to mu naught I enclosed. So similar to Gauss's law, this is only useful for symmetric cases. But there's only 2 types of symmetry we see in magnetic examples with currents. What are those 2 examples?
Well, the one I know we don't use is the circle one, right? So it would be plates and cylindrical.
Exactly. So we have sheets of wires, so infinite planes, and we have cylindrical cases, so just individual straight wires or like layers of wires that are cylindrically symmetric. So if we have an individual straight wire, how do we get the magnetic field using Ampere's law? If a single wire carrying current to the right. Actually, screw that. We're going to have our wire coming straight at us. It's going to be out of the page.
Well, let's see. So it's a wire, and we're trying to look for the magnetic field. Wouldn't that be B is equal to U naught I over 2 pi R?
Mm-hmm. And how did we get that from Ampere's law?
From Ampere's law. Oh boy. Uh, actually, I think the I would be I enclosed in this case.
Who cares? You've got it.
Let's see. I don't. No doubt it's by deriving stuff, but let's see.
How do we go from this integral here to mu naught I over 2 pi R?
Well, let's see. B is a constant, so we move that out.
Mm-hmm. And, well, first we need to get rid of the dot product.
The dot product in this case, since it's always going to be perpendicular to it, it should just be B times DL.
Exactly. So B comes out. Integral of DL. What is our Amperian loop? What is L?
Ooh, the loop. Crap. In this case, it should be the cylindrical loop, right?
Mm-hmm. What would that be?
That would be the 2 pi R, right?
Exactly. It's essentially our circle surrounding a part of our wire, and the perimeter of a circle, that's definitely a very symmetric circle. Symmetry of a circle is 2 pi R. And so what...
Okay, yeah, and then DL becomes L, and then you just divide that L
exactly
with the U naught I enclosed.
So B is equal to mu naught I over 2 pi R. And what direction is B going to be in?
You have to find that out in the right-hand rule.
Right-hand rule. How do we use the right-hand rule here?
Okay. So we know I is out of the page, and we're looking at from a wire, so it should be the fifth one. Mm-hmm. So thumb out of the page, counterclockwise.
Exactly. It's going to be wrapping around our wire like so. You might see this described as phi hat if you ever take like an upper level E&M course, because it's like with cylindrical coordinates where you have R and you have phi and you have Z, or theta hat or whatever. We usually use phi though because theta is usually for cylindrical coordinates.
I think I actually have seen that in a math course once.
Yes. Might remember from what course was it? 225? Whatever multivariable calc is.
Yeah, I think it's just when I saw that, I just freaking sticking with XYZ. I don't give a damn.
Thing is, you don't have a choice sometimes. Sometimes you have to do things in other coordinate systems. Oh no!
Yeah, get the computer.
Get
a graph.
Simple,
get a graphic thing.
Symbol Lab, help me.
Yeah, basically. Well, I think it would be more like GeoGebra or something like that. Like, actually making the graphs.
Yeah, help you visualize it.
Yeah, making those 3D graphs by hands are a pain.
So, that's Ampere's law. What is Faraday's law?
That has to deal with the EMF, right?
Mm-hmm.
What did I do there?
So, you mentioned something about flux earlier.
Yeah, that would be the magnetic flux.
Mm-hmm. So we have this formula here, B dot dA.
Yeah.
It's the same thing as for our electric flux, like with Gauss's law. So, what is Faraday's law?
Uh, all right, that's the time he called in sick.
Mm.
That's why
Oh
everything's so
yeah,
loose.
that's right.
Let's see. Magnetic flux, electric flux, yada yada yada. Where the heck is that? Oh well, there's Lenz's law too. Oh right, a minute. Okay, Faraday's he on that part he talks about at the very end, which is weird. If everything loads. I'm at the part, it just needs to load. Okay, so Faraday's law, it's because I wanted to make sure it's a changing in the magnetic field producing a changing magnetic field produces an induced electric field, and that is uh it equals to the magnitude of d. I don't know why I was struggling there. DIB basically d of the magnetic field over dt.
Not magnetic field,
Magnetic flux. Sorry.
magnetic flux, exactly. So the change in a magnetic flux, usually by the change of a magnetic field, but not always, the change in the flux creates an induced EMF that is related to the magnitude of our EMF is equal to the change in flux over change in time. So that's Faraday's law. That's about it. I mean, there's a bunch of different examples that you can use Faraday's law to derive some, one of the other specific examples, like motional EMF or our rotational EMF. But I think we don't have to touch on this too much since it's still pretty fresh. I mean, I think it was just our SI Pass session on Sunday, right? And you had your quiz Monday. I think
Yeah,
it should still be relatively fresh in your head, and I think
relatively.
I would think maybe he would be slightly less focused on on the material that's so recent because you literally just covered it. I think
Thank
maybe
God. That rotation stuff was annoying. That quiz with that rotation triangle was awful. Ugh.
triangle. Oh, do you mean the triangle inside the magnetic field?
Kind of, but instead of going into or out of the page, it was like in the same direction of that triangle. It was like to the right, and that was just like, oh, the
Hmm.
way. And then got it wrong because I think we assumed that where it was at was the original position.
Hmm.
It just, yeah, ugh,
Sounds like no fun.
it was not.
So I'd
Even though I got 7 out of 12 on that, that was not my lowest quiz. My lowest was 6 out of 12.
Yeah. I'd say so these are pretty important. I'd say there's just one other thing I think would be important to know for magnetism is the idea of a magnetic moment. What is a magnetic moment?
Oh, magnetic moment. It's not with the VL. Oh no, that's it. That's inductors. Magnetic moment. That's the density. Okay, magnetic dipole moment. So that should be mu is equal to NIA.
Yep, mu is equal to NIA for what specifically? Give me some context.
Oh crap. Okay, I's the current. A should be the direction of the area, I believe.
The area vector for a wire loop.
And is that the number of turns?
Yes, sir.
No. Oh, it
Yes.
is. Oh, okay.
Yes, it do be the number of turns of the wire loop. So, if we
Okay.
have a wire loop, and let's say it's doing a little bit of this, and so its current is going around like this, and we have a magnetic field that's to the right. What's going to happen to our wire loop?
Wait, what? So
we have our wire loop, and we have our magnetic moment. What is going to happen to it if it's placed in this magnetic field to the right?
it will rotate that way?
Yeah, exactly. The magnetic moment is going to be rotated down towards the magnetic field. There's going to be a torque on it that's going to cause it to rotate. Fun fact, what direction is the torque if it's rotating like so?
Oh God.
Right hand rule. Come on, you can do it. You can do it. You can do it.
Okay, so question is the dipole pointing up or out of the page?
Dipole's pointing up. Magnetic field
Okay.
to the right.
Okay. Fingers up, right. So torque should be into the page.
Exactly. Torque here is into the page. I'm gonna draw this bigger. That's pretty much it. I think that's, sort of, we've touched the surface on all the main concepts you'll need to know for the quiz tomorrow. Obviously, we weren't able to cover everything since we only have an hour. But I think we take a look at this little cheat sheet. It covers most of the important stuff. And you should, at least you, will absolutely definitely have everything you need in order to get that B.
I mean, I just need 5%.
Yeah, you could check out after the first quiz.
Yeah. Oh, so we can actually meet. Wait a second. No, I think he did say it will take time. So. But, I mean, the circuit ones, I should be okay.
Yeah. I think,
As long as I don't mix up my capacitors and resistors. But I definitely should be okay on that.
yeah, your circuits, you're going to be completely fine. Here, I'm going to go ahead and draw some borders on this stuff. That's no good. Cool. Borders, yay! Separation, organization. All right. Well, thanks for coming in, Roger. You have been to every single session of the semester.
Hey, it has been helpful because seriously, some of those quizzes would be lower if it wasn't for this size.
That's true. So, good luck studying for tomorrow, and perhaps I'll see you around sometime. I don't know. Are you going to be? You go to UMBC, right? You're not one of the students that's like taking the class while going to another school.
Yeah, I am going to UMBC, so, and I should be going to I hopefully will be going to those campus classes.
Mm-hmm. Are you gonna be living on campus or?
No.
No. Okay, you're gonna commute.
No.
Yeah, my brother's moving in a week and a half.
Then
Still got another 2.5 years probably until they graduate. All right, I'm gonna go hop off and prep for my 121 session. Good luck studying. Salute, soldier. Stand up.